Okay, so
We will have now the continuation of Arnab's talk, our own Arnab Bhattacharjee from Charles University, and he will speak about q-deformation of Kostant differential for the A-series irreducible quantum Planck manifold.
Thank you very much. Okay, so the overview is like this. So first I will talk about Q deformation of Kostant differential. Uh, Second, the Q graded Hopf algebra structure on quantum exterior algebra. Third, Q deformation of twisted dynamic differential. And fourth, I will talk about some questions towards the BG sequence. Okay, so here I should mention in the beginning there will be a little bit of formulas, big formulas will be there. So I don't want to annoy people, but still, I mean, I was uh, mentioning. Yeah, so here I start with the OQCPN and define the contraction map. So this is a map from so theta upper I, as you already see, is the generators of n plus, and theta lower I is for the generator for n minus. One can define the Q deformation of the contraction map from contracting kth power of n plus to k minus 1 power of n plus in this way. So this is so here I have mentioned this Aj is the coefficients which which actually comes when it actually tells you how much amount of the power of Q will come out when you contracting by the nil radical. I mean, you are eliminating one of the kth one of the kth generate elements by the help of n minus. So yeah, so that's it. It will tell you how much amount you have to pay for eliminating this guy. So first of all, this is you can show this is UQL equivariant. So by the way, so whatever I will talk about first or second part of my talk, I will mostly talk about the equivariance of UQL on most of the maps. So here the Levy the contraction map is EQL equivariant. The meaning is this, and using this equivariance, you can find explicit the relation between these coefficients, and you can see how much exactly the amount you are paying, the power of Q is coming while it's coming out or for the elimination process of theta I H. So why we need this contraction map? Because of this the Kostant differential. So we consider V to be a UQG module and pi is its representation. And then Q Q deformation of Kostant differential is defined from the kth power. It's going to kth power of n plus twisted by V to k minus 1th power twisted by V. So we are just using the contraction to contracting the power. So if you can look into the formula here, so this the contraction which is given by the n minus is we use its corresponding the n plus the dual representation part what I was showing few minutes before. So this guy is the dual representative of this theta j.
This contraction map. So is this basically injecting the wedge product into the product and then just pairing the first two? Because
exactly. If you look like here, sorry.
Tender to pair the first two and then wedge.
Yeah, so we just need it to cut in this.
And this is just for a general Grassmannian.
This is for the general, yeah. Yeah, I mean, I was thinking, okay, there are lots of big formula. I shouldn't make people more annoyed, but in the end, I mentioned only for the CPN. So People can find it out for the general Grassmann. It's possible. Yeah. So this is what I'm saying about this Q deformation, and you can square it. It goes to 0. It means it forms a complex, and it is also UQL equivariant. All right. So, for example, I mentioned for the case of Grassmannian 4-2, but yeah. So I think I should skip this because I haven't mentioned, but I can mention well, no problem. So the thing is here I have mentioned theta 1, 1, theta 1, 2, theta 2, 1, and 2, 2. So the representation, I should mention it here how it goes. So for the Grassmannian 4-2, you have 4 cross 4. And if you look into the Dynkin diagram, so you are crossing the second one, so 1, 2, 3, which means your levy is given by these guys and these guys, or more precisely, this is your E1, E3, F1, F3, and K1, K2, K3, plus minus, plus minus, plus minus. And this part is your n plus, and this part is your n minus. N plus, n minus. So if you look into this part, how the representation theory looks. So if you index it by theta 1, 1, by this guy, theta 1 to this, theta 2, 1 this, and theta 2 to this. So this is your E2 representation theory. So this is E1, E2 with some commutator. This is P2 with some commutator Q, and this is P12 or 12 with the Q commutator. So the representation theory works like this. So here theta 2, 1, you're acting on E1. Here you are acting on E3. Here you have E3. Here you E1. So things get into the two-dimensional array, you can say, because for the CPN, we saw that it's just a line, it's one-dimensional. So here things get a little more complicated, and you have this two-dimensional array picture here. So yeah, so this is our theta 1, 1, theta 1, 2, and 2, 1, and 2, 2. No. Okay, so I have mentioned, I didn't mention the case here also, yeah. Yeah. Here K1, K2, K3 inverse, here K2 inverse and K3 inverse, yeah. And classically, there are no cases. No. And similarly, one can find this second wedge power of n plus the same way we were describing before, but you have to be very careful about your indices. So it says I1 has to be lesser or equal to I2. If it is equal, then J1 has to be strictly less than J2. And same goes for the J's. So again, it will satisfy the classical picture what Ray mentioned just few in the comments. For example, it should be so the dimension of the second wedge power, it should be 4C2, like 6. So since we have the description of the second wedge power of n plus, then we can talk about the contraction map. So the contraction map should look like this. So we are contracting from second wedge power to one power, which means the n plus is in this way. Okay. So similarly the constant differential, you can see we can define the constant differential from the second power to first power. You can see the main difference here, the coefficients. So this is the coefficient in the which tells you are in the two-dimensional array. If you compare with the case sorry, if I go back here, you see if you look into the coefficient, we just have the coefficient in terms of j. So and here we have the coefficient in terms of I and j. So if you put your I is 1 and j keep as it is, you will go back to your case of your projective case. Yeah, so it also satisfying the square is 0 and the Levy equivariance. And the most interesting part, I think, in this case is the commutation between uh, these generators, because at some point it's very helpful to have this relation between uh, the generators of this positive nil radical. And you can see in the last part, it's very interesting for the case of Grassmannians, because it talks about the diagonal and anti-diagonal part. So here you see theta 1 1, theta 2 2, 2 1 and 1 2 and 2 1, which is very complicated. And similarly for the same kind of relation one can find for the negative radicals. But yeah, I mentioned only for the positive ones. No, that's the interesting part, because you see, so what happens for the Grassmannians, even if you calculate the relation between the, how do you say, the generators at the level of the cotangent space and all those things. It's the diagonal and the anti-diagonal parts are the main tricky part. So yeah, I mean, these Qs are really, yeah, I mean, it's actually the calculation, one can say. And this commutation is basically tells you there is no Q in the first part of this commutation bracket. But anyway, this kind of relation is very helpful in this type of calculation. So I thought it's very worth to mention. Yeah, so then since we have this Kostant Laplacian, then one can talk about the adjoint of Kostant Laplacian. But before that, we need the pairing between this n plus and n minus. So I talked about the pairing about n plus and n minus, and similarly one can find it's already I mean it's one can find for the pairing of this kth power of q and kth power of n plus and kth power of n minus. So and how can you find this? So so what I'm trying to say is we need the inner product on this guy, but we already know this isomorphism exists. So this tensor iso to C. So sorry, should be other way. So from here to here, one can find this guys. So which tells you can find your the adjoint, and if you so adjoint for the CPN is in this way, and if you square it goes to 0, and it's also the UQL equivariant. So the obvious thing after doing this, after having this adjoint, is the Laplacian, which comes from this Kostant differential. So here we need the Laplacian to get something, which I will tell in a few moments. So del q is the Kostant q-deform Kostant Laplacian, and because this Kostant Laplacian, this Kostant differential and its adjoint are UQL equivariant, so in principle it has to be its Kostant differential has to be the Kostant Laplacian has to be the UQL equivariant. And once one can do some simple computation to find the second point, which tells you the image the image of the Laplacian of image of this adjoint of Kostant guy is contained inside the image of the adjoint of the Kostant differential. And then one can prove this, not only this lands, the image of this particular space lands into the image of partial Q dagger, it's also invertible. And then we will like to shift in the language of cochain, because we will be heading towards the differential complex of cochains. So we will, from now on, we will call or write everything in terms of these cochains. Here you can see this cochain in Ck n minus V star is finally gives you this kth wedge power of n plus tens of V. And then there are some technical stuffs are going on. You don't have to bother too much about this. But yeah, so here this I have defined this operator QQ, which is defined on Ck n minus V star to Ck minus 1 to Ck, which maps the image space, which maps your Ck minus 1 to the image space, which image space means the image of this del Q dagger. And using this QQ, one can define another operator SQ. So it's basically the technical part. And the most important properties one can see is in this lemma. So this is a very interesting part. So for example, SQ, image of SQ is contained inside the kernel of partial Q dagger. The second one also, and the third one is also interesting. It tells you your SQ is the projection. And then another thing we have the canonical projection. By the way, so one thing I should mention, all these things, it's built upon the Kostant differential, and all these operators like QQ, SQ has to be UQL equivariant. Ray, do you have any question?
Actually, yes.
Yeah.
Remind me what Q is. Big Q, not small Q. This one I know.
Yeah.
But
yeah, so this is the Q.
big Q, please.
Big Q. Okay. Do you have any other question? I mean, is kind of technical part, I would say.
So it's important in English.
Yeah.
Now you're defining. Okay, yeah, no, okay, good.
Okay. Yeah. So we have the canonical. If you go to the last part, so we have the canonical projection from set K to, so it's ZK, means since we are talking about the cochains and all these things in this language, so it's a kernel of partial Q dagger, and canonical projection tells you it lands to this HK, which is the quotient of the kernel and the image. Because our sequence is decreasing, that's why I take the k plus 1 instead of k minus 1. And more. Oh, yeah, no problem. And one can prove this is this projection, the canonical projection is UQ, and this is very just 2-line proof or 3-line. And finally, we should know the kernel of this projection, because we are landing towards this the sequence, the cochain complex you are seeing you have here. So the lemma says the kernel of this projection composition SQ, I mean this guy, is the image of the del Q dagger on the level of k plus 1. So what in the end we are doing is, we know the first line, we know we have the Kostant differential. And in the end, all this machinery, what we have done in the last slide or the slide before, it's actually to get a UQL equivariant differential complex on the cohomology classes of UQL models. So this is the part we get from Kostant differential. Now one can ask, can we lift all these ideas at the level of UQG, where the question about BGG comes into picture. But we will talk about in the end of this, we will address this question in the very end. But yeah, so this is the second part. So it's Q-graded Hopf algebra structure on quantum exterior algebra. What does it mean? So we consider V as a finite dimensional type 1 UQLS module and a unital graded algebra. This is the quantum exterior algebra of this quantum wedge powers of V's. It's said to be the Q-graded Hopf algebra if it has coproduct, co-unit, antipode with a graded multiplication. What do I mean by this grading? So this is the main the point of what I mean by grading, not the grading we have at the level of this quantum exterior algebra. Classically, it gives you the Z2 graded picture for the wedge product algebra. And the most interesting part of this is in the second point I have mentioned. It has to satisfy because it's a UQL module, so it has to all the multiplication, co-multiplication, co-unit antipode has to satisfy the UQLS action.
You don't specify the coproduct, you just say there should be one.
Yeah, so here is
so that's the one that you get from the tensor algebra.
Yeah. So first we define the coproduct for the degree 1, and then we will build upon for the other degree forms. So for example, here we found we have the coproduct for the degree 2 wedge powers, and so if you multiply, if you do this wedge multiplication in the third line, you will get this. And from second to third, you are actually using this graded rule, what I have mentioned previously here. So what you have, you actually split your coproduct into various levels, or you are basically you're grading your coproduct. So for the level of degree 2, we have the three possibilities: 2, 0, 1, 1, and 0, 2. 2, 0 is the first one, you can see, and 1, 1 is the middle two terms, and the 0, 2 is the third one. So in this way, you split your two forms in the graded components like 2, 0, 1, 1, and 0, 2. So from here, one could expect to do this kind of stuff for the general degrees. So here we get this definition. So it's about the wedge coproduct. So you're basically splitting your coproduct into various levels. So this is a map called delta k comma L from k plus L to lands on the tensor product of k and L, such that this second condition hold, which means you coproducting, you are having the coproduct at the level of R forms. It should be like this. So it holds for every forms you choose. And not only that, the main idea is to have the explicit version of this wedge coproduct. So this is the second point. One can try to find, one can try to write this this k plus L form like in this way. So here we are actually doing some combinatorics basically. So here so here I have choose the set index set I and j in such a way that there is an ordered pairing between these i's and ordered pairing between these j's. So vi is it represents the k form, and the second it represents the L form. So you are basically having k plus L form, you are landing to k form and L form. Now the main difficult part is to describe this this coefficient aij. How you get this or how do you find this aij, or how to relate this aij with some the relation between this I and j. So it one one can do this to find out the relation between this the coefficient depending on the index that you choose by using the co-associativity of the coproduct. But there is a very long formulas for the ages, so I thought it's might be good to give some examples. So yeah, for example, if you take the case of when k is 1 and L is also 1, so you are basically talking about at the level of degree 2. So so what you are doing is maybe I will erase this guy, or maybe I will put here. So what you are doing is you are in two form for k equal to 1, L equal to 1, to V. So this is your 1, 1. So this is your 1, 1. Sorry, not 1, 1, 1, 2. This is 2, 1. V2 tensor V1. So this is the very basic case what one can try to show. And this is nothing but minus q inverse of 1, 2. So, and similarly, one can compute this kind of relation on the third wedge power of V, which lands to second wedge power of V and tensor V, and you can also have. So the main point for this particular remark is, depending on the set of indices I and j you choose, you can have the relation between ij's, and this could be found in more generality, but there are lots of formulas because of this combinatorics. Okay, so then because we are talking about the wedge coproduct, So one could ask what is the meaning of co-associativity in this language. So this is the meaning one could find in this lemma. And the next one is, since I mentioned all the structural properties should satisfy the Levy equivariance. So this is the first point to start, where it says one can prove this your wedge coproduct is Levy equivariant. Yeah.
Go back.
Yep.
This associativity, when you have the tensor product, it really means that you're taking the tensor is Q graded, as you say.
Yeah.
Right. I'm curious how this graded tensor product related tensor product, because in one of the papers is your supervisor realizes this gas is equal algebras. And they
Okay.
graded whole algebras into
Okay.
then you, instead of this looking artificial Q gas,
Uh-huh.
you have some braiding, and it automatically defines
This kind of relation.
Positivity and equivariance.
Ah.
I'm curious now.
So maybe these two are related. Yeah.
Well,
I guess you can go from this braided powers to your tensor product, and then you can go vice versa. So I think one can.
So you use it some negativity constraint.
Yeah.
It allows you to do one thing on another. So it's you cell invariant, and then you. I'm now curious. Is it the same that we found?
Probably. Yeah. 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 So this is okay. So next we will talk about the contraction map. So this is the same idea. So I will not repeat again. Why we'll need this contraction map here? So because of the last theorem here I mentioned. But before that, I should also mention that this is UQL equivalent that we already have seen in the context of the nil radicals, and this is for the any UQL modules. And the second theorem is tells you about the UQL equivariance of identity tensor, this contraction map. So this is the second result. It tells you about the relation between this this wedge coproduct and the contraction map. So classically, if you write down things here, you will get this -1 to the power some k or k plus -1 to the power k plus 1. In the quantum case, it's is the minus q. All right, so this is the relation between the contraction map and the wedge coproduct. And here everything is UQL equivariant. This guys and this guys and this guys, all this. Here we will define the co-unit and antipode. So co-unit is defined is like this. So if your the Q form has degree more than 0, then epsilon of that guy is 0. If it's 0 degree, so it's 1. So it's the degree, the bracket, that guy is. And the antipode is given by on the degree 1 is minus u, and you can construct by this way for the various degrees by taking the minus q to the power minus degrees of v and w. And next theorem says it's this.
So here I have a question. This should be a linear map, right? So I guess that you said that so epsilon on 1 should be 1, and then epsilon on, I don't know, 5 should be 5. I guess that you don't set it to 1 in degree 0, but you're saying it's
Yeah.
the map that's determined by being pretty tall.
Yeah, true. Yeah, it's had to be defined from the And these guys are this unit and co-unit guys are it's co-unit and the antipode are UQL equivariant. And then we have the following lemma here. So which tells you about the interaction between the antipode, the multiplication, and the co-multiplication, all the structure maps we need. And the second is another structure map represent relation. So here tau is the flip, but it's twisted by some q's. So this graded algebra, what we were discussing, I just mentioned, is has coproduct, co-unit, antipode structure. All these things are UQL equivariant. So this gives a structure of a Q-grade Hopf algebra whose structure maps are Levy equivariant. So the Levy equivariance in this context is the main important thing. Okay, then q-deformation of the twisted DRAM differential. So here, since I mentioned in the pre-seminar the what would be my setting. So here you can see classically what we have is P plus is the direct sum of this Levy and the positive null radical. So you can describe its q deformation by taking which is generated by this EI, FS and KI inverse. So the main difference you can see is in the E's. So whatever the node you crossed, the corresponding EI you are actually considering in the case of P plus, which is the thing you are not considering for the Levy. And this is actually comes from N plus. So for example, for Grassmannian 4-2, if you are crossing the second one, Grassmannian 4-2, you are crossing the second one. So Levy, you are only having 1 and 3, E1 and E3, F1, F3. But for UQP plus, you have to take E2 also because you are considering N plus. And N plus is inside the N plus, E2 is actually generating your N plus. So you have to also take this as a generator. So this is the description of UQP plus. And then we will talk about the generalized Varma modules, which is the geometric picture would be the homogeneous vector bundles. If you take your Lie group G and its parabolic subgroup P, then one can define this homogeneous vector bundle, and this is the algebraic picture of on the level of Lie algebras. So yeah, so this is the way you are basically taking the tensor product UQG and V, and you are considering the relations. Here it is the relation, and then when you talk about, so I mentioned in these 2 points, when you talk about the one dimension, when you are using one-dimensional representation of UQP plus, here I use this kind of notation, Varma CQ lambda. And for the co-chain complex, what we described in the case of Kostant q deformation of Kostant, it should I take the notation of this Varma CK n minus B star.
All what fits small
Small k. This k is the degree of the wedge power. This is the capital K, I mean the usual generators K. This one.
also displayed.
Okay. Yeah. You are right. I should. Yeah. It makes me a little more confused. Yeah. So this k is the. I mean, this k is the degree of the n plus, and I should not mention this k, but it's it's a typo, I could say. Yeah. So yeah. Which where?
In the definition, you say UQ dot G tensor B over IK G of B. Right.
Yeah. That's the point I was saying. This is the typo. Yeah.
That's the typo.
That's the typo. Yeah.
Definition
Yeah.
of typo.
Sorry.
That was my next question. Okay.
Yeah. This is the typo. Sorry. Yeah. This is the typo. Yeah. So this is the generalized Verma modules. Then we will define the q deformation or twisted DRAM operator on this Verma modules, which is given by this. So here, if you look into the formula, so it has two components. The second component is given by the Kostant. So you remember we are in the Verma model, so you have UQG tensor, the other guys. These other guys are the object for the Kostant differential. So this, so there is, so it's, there's a contribution which comes from the Kostant, and the second contribution which is happening at the level of UQG. So here the main difference you can see, theta I, I'm contracting my theta I and I put it back. So I mean as a left action. So here this is 1. So theta I is acting on the left side and gives you this guy. So in the DRAM differential, you have two contributions. One of them is from the Kostant. One can show the square is 0. And okay, so there is also possible to, yeah.
And this map is UQG, UQG module.
You mean the preservance of the UQG?
Delta DR.
Yeah, you mean the if it is satisfying the action of UQG? That's the question. So this is I will address because this is a very interesting question which will lead to BGG. So wait. So it will be enough to define on the level of. So if you, that's what I'm saying. I mean, okay. So you are asking why I took the 1.
Does that mean the whole norm is UQ?
Yeah. So because yeah. So it will be in the next slide because when I define the action of UQG, so probably you can find it from there. So it acts from the left and it generates your whole module picture. Anyway, I mean.
So the question remains if the differential is linear and corresponding to the action.
Yeah. I mean, it is linear. It is linear. Yeah. It is linear. Yeah. Okay. So the action of UQG on the generalized Verma modules is in this way. So EI acts, EI, FI, KI all acts from the left, and it's a left multiplication. So it's unusual than the UQL module action we see for the modules like n plus or kth power of n plus or n minus, something like this. So this is nothing new. So it's already in the literature. So but in the end, one can prove if you consider your x from the levy. If you consider your x from the levy, so this is for the UQG, but if you consider your x from levy, you can describe your action by using it's the x1s and x2, which comes from the Schweitzer notation and taking the co-product. So it's the adjoint action on UQG, and the second part acts on the module side. So this is precisely for the action of UQL. Main problem is because you see this is a balanced tensor product of UQP plus. So here EI is, if you act EI from the left, if you can manage to bring across to the right, then you can bring it back to here, because it's balanced over UQP plus. Main problem is with the Fs. Even if you can move it to the right hand side, you cannot bring it through. This is the main problem happens in the Verma module settings. Okay, so now I will talk about the differential calculus on Verma modules. Ray, any question so far? Because I think Ray has some noise. Okay. No. Yeah, so differential calculus on Verma modules. So we define the before this differential calculus, we will define the wedge coproduct that we have seen in our previous section for at the level of UQL. Now we will like to define on the level of UQG, on the Verma modules, which is defined like this. Well, I could mention why I take lambda equal to lambda 1 plus lambda 2. You can take whatever lambda you want here and here, but when the main point is, does it satisfy the UQG equivariant? So from that point, because this guy, if you take here lambda, lambda prime, lambda double prime, this guy in the end will be equivariant, UQG equivariant, if you have lambda prime and lambda double prime, the sum of lambda prime and lambda double prime is lambda. That's why we started with this lambda equal to lambda 1 plus lambda 2. So which is defined, your wedge coproduct on this Verma is defined in this way. So this, the middle one is the wedge coproduct you already seen at the level of UQL modules, because we know n plus, any wedge power of n plus is UQL equivariant, UQL module, so we can bring all the theories to in this framework. So it's a one-dimensional representation of UQP plus. Yeah, sorry, I should mention, I am dealing with the one-dimensional. This is not the twisted by some general V, because what the formula I will going to show, it's nice if you take the twisting by one-dimensional representation, but if you take the general V, it's a mess actually. So yeah, so this guy is a UQG equivariant, and this is the graded Leibniz rule, which holds because of the reason, if I go back to this guy, if you look here, this is the main idea why for the graded Leibniz rule. So you have the relation between your wedge coproduct and the contraction. This helps you to prove your graded Leibniz rule. And here you see this gradation is this particular object is actually coming from that formula.
So really a different calculus is more like a different co-calculus or something.
Yeah, so yeah, you're right. So I should, I forgot to mention, probably it should be co-Leibniz rule, graded co-Leibniz rule. It should be graded co-Leibniz rule. Yeah, you are right. Yeah. So this shows that we have a differential co-calculus and I mean this co-differential calculus on this one mass. And
Because it is a differential, right? So it's kind of a differential co-calculus.
sorry, differential co-calculus, yeah. Differential co-calculus, yeah. Right. And yeah, the main thing is this. So I was talking about this Dirac differential. We have two components. Here, since you took the one-dimensional guy, it means your constant has no role to play in this picture. Because if I again go back to the formula, well, I should go back to formula here. Here you see that in the twisted part is the action is due by the positive mean radicals. So when we know when for the one-dimensional case, the action of this thetas will vanish, which means we are end up with. So we have this Dirac differential, two components. When we take the one-dimensional representation, this we do not have any contribution. So only contribution which comes from this guy. Now the interesting part is the second point. So our objects are like this, and it's isomorphic to n plus. It's the graded half algebra. And if you consider it as a UQLS module, then you take the dual. The dual guy of this object is the objects we use in the Heckenberg calculus. So which means we have a differential co-calculus, I mean, in the dual picture, which is the dual picture of Heckenberg calculus, basically. If you look these guys as a UQLS module, because you remember this picture, this to this only UQLS. But you can see also these are also UQG module. There the problem starts. If you consider all these guys as a UQLS module and think of this picture, it tells you about you are actually doing Heckenberg calculus in the dual category. But you recall I was talking about the question of can we have this the cochain complex I mentioned my beginning slides. Can we do or extend this kind of setting, this kind of stuffs towards the UQG? Because Heckenberg calculus tells, or their picture tells, you can have this beautiful equivariance at the level of OQG or UQLS at the level of UQLS. If you consider from the level of Lie algebra is UQLS, it can be done. But so what the question is can be done for the UQG. So here I mentioned the reminder of this cochain complex, and I put this question. So the natural question, can we lift this equivariant differential complex like this? Can we have this kind of cochain complex and this projection down to the cohomology chain, this cohomologies? So then so there is lemmas which which tells about this. So DRAM differential, classically, if you look, it happens. It does. You can do it. You can talk about this kind of lifting. Yes, but in the Q deformation case, many things it's not so obvious. For example, here I mentioned, however, in the Q deformation case, the DRAM differential is more delicate and becomes equivariant under the action of UQG because it. So this is about the equivariance of the this whole DRAM. So you have this UQG modules, you have this DRAM. Now you are asking if this DRAM is equivariant under the action. Yeah, yeah. So I'm saying that it depends. So this lemma says that it depends on this. Sorry, this eigenvalues lambda k. For example, if you define your Varma and you sorry, this one, this theorem. So if you define your Varma from Ck to Ckn minus 1, it tells you you can have up to UQG equivalence. These two eigenvalues has to satisfy. For example, if you take lambda k and here mu k, and this UQG equivariance tells you this lambda k and mu k has to same. And the precisely your lambda k for OQCP, the projective case is this. No.
You can take any character of the sample, of the sample in person building, and then you define your one-dimensional model. So you can have any weight. With some conditional weight.
So say it again, question.
So for these one-dimensional models that you induce into inducing. So you started as a guy was a robot, right?
Huh?
So these one-dimensional models are classified, well, if they are type 1, they classified not by a single complex number, but by the tuples of numbers, which are basically weights. It's on the algebra level, you take a map, do any functional from Cartan complex numbers, and then so you have a huge family from them, and you can weigh the one place.
I mean, at least this setting, this actually depends on this particular eigenvalue.
Yeah, but it is now eigenvalue for the center, and the rest is so. Yeah, could you please remind how we define that on the C?
This.
The central guy is a.
Okay, so here is this action of UQG, for example. Yeah.
C lambda. So lambda was
No, I haven't defined for the C lambda because I defined it for the general V.
The C lambda is a one-dimensional model.
Yes. Yeah, and if you have, for example, if you take your E's, which are from the UQL, it will brings you to this left and right hand side, and it will vanish because it's in a one-dimensional case.
Yeah, how case C lambda.
So q to the power lambda. So the Kc, which is the center of the levy. Yeah, yeah. So this acts on 1 lambda is q to the power lambda and 1 lambda. Yeah. And Ray, could you repeat your question? Probably I didn't understand your question before. So probably here you had the problem. So what I am trying to say, so this is a module map. If you have, yeah, it's a particular for V. Yeah. So I should.
Yeah, module map and for some V's not.
In that case, it's not defined.
Yeah,
It should be a module.
And the question would be.
it should be for one dimensional. It has to be particular.
So that means, and that, how is this map defined if it's not one of those special cases?
Uh-huh. So yeah, in this case, it will be just 1 tens. Here it will be 1 lambda. V will be replaced by C lambda in this case. So
It's asking for a general capital V. You have the definition of the delta here. And in the formula, you have a 1 tensor something. What would happen if you do not plug in a 1, but any element of U here? What is the, it would be clear to the left linear map, but just extend as a left linear map. But if it's not left linear, it seems to be not left linear, what would be the definition?
Classical case is partial map.
and this is the same way classically could be done.
It's just and it's margin. Yeah.
Yeah, I mean it has to be. It has to be. Yeah, it has to be.
So could you go back to?
But this lambda, this lambda k, it depends. It's actually coming from the action of the crossed node. I mean, for example, if you cross for Grassmanni and 4-2, you cross the second one. So F2 will give you this this particular lambda k.
It's proved by it's a model map. It's not, it's model maps and. Yeah, that's what I'm, so I mean, before it's not properly defined.
Okay.
This is actually around the.
Same number, that's why
If it's not the same numbers, then it's not. But it's the consequences of the fact.
Yeah, so it depends on the degree. So you cannot expect this. If I go back, this kind of chain at the level of the UQG variance. So which means everything fails at the level of UQG. I mean, all these theories, if you translate into the settings of the UQLS module, everything works. But whenever you translate everything for the setting of UQG, things doesn't. That's the main think I'm clear. Yeah, so that's the end of the talk. So yeah.
Do we still have some more?
Yeah, thanks for the nice talk. I feel so. I have actually many questions, but maybe I just ask one. So, since you said this is something like dual to the Heckenberger calculi, should I think of these like as vector field calculi, or is Werner modules something different?
Yeah, it's the vector field calculi. Yeah, I mean because Varma is the, if you look into the geometry picture, it's the comes from the homogeneous vector bundle. So from that point of view, yeah.
But if it's like vector fields, then I would expect maybe also some Lie brackets and things for vector fields.
The Lie brackets, I mean, in this case, we do, or the main philosophy is to, what's the replacement of this Lie bracket is the left adjoint actions.
Mm-hmm. Good point. Yeah.
That's the philosophy.
Yeah, I think we were starting to conversation. So maybe I'll ask one question. So then there was the, as you know very well, the BGG paper of Heckenberger and Cole, where they made a dual construction of their calculus, so in particular this for CPN for the Grassmannians. How does what you're doing relate to what they did? I mean, it should be very similar.
For example, here in this, if you if you consider these guys as a Levy module, so which means you are here, so you just translate everything here. So you are here means you are having the Hilbert.
They also had the Verma style complex, and then they dualized in the same way that you dualized. So the two things should be very closely related.
Yeah, I mean,
Are you possible? Is it like an alternative description of what they have done?
but they did for the in the language of the Lie groups. I mean,
But they also then later on they did it in the language of Verma modules. That was the last in their series of papers. So first of all, they did it as you've written, OQG, cotensor, Veep, zero bullet, and then they did it dually in terms of Verma modules and sequences of Verma modules. So it looks like you're doing something extremely similar, maybe just more explicitly. Which I mean, it's good to have a more explicit version of what.
Explicit formula because
Sure. Yeah. So possibly it's like a more explicit presentation of what they
I mean,
found.
when I was discussing this with Peter, so he was trying to build this kind of stuffs from the Lie algebra side. So they did for the Lie group side. So his idea is to build from the Lie algebra.
So yeah.
So I think what is happening in the paper of Beckenberry and Kolb from 2006, where they take this sequence of Verma models and dualize is. So what is the difference between what you are doing is they are not considering a co-product on the Verma module side.
Yeah, true. I mean, these guys, they are not, they haven't used. Yeah, I mean, this formula could be written quite well manner, I would say. Yeah, that makes more confusion. Yeah.
differential presentation, right?
Yeah, I mean, that would be sure.
So. More questions? Is there anything online? There. Then, yeah, and again. Well, once a week, we have this it's Stefan Waldman from the University of Würzburg, and